Here's an interesting problem when you're dealing with vectors and work. I like this problem. And if you have studied physics, you might have run into something like this. But if you haven't, it doesn't really matter. My assumption is that you kind of know what the definition of work is. So you should know that work is the actual dot product between a force and a displacement. I'm going to use displacement as S. So basically it's the energy transfer that goes to an object or from an object when you're applying a force along a particular displacement, and that is captured by the dot product. And if you've studied the dot product, you can go ahead and do this particular example. Now, what I want to be able to show you and what I want you to think about to kind of break down these work type of examples is to take a box with a mass of 10 kilograms, which you see there on the right hand side. You have the same identical box, just replicated, at the bottom of the ramp there. And what we want to be able to show is that the actual work that you need to do to get this box to the top of the ramp, basically either by pushing it up or pulling it up on that ramp, or by just simply lifting that box, okay, all the way up to the top. So what I mean by that is if you would take this box, you would just lift it, okay, right there. You can of course put it. So our interest is how much work is being done, okay, if you're going to be lifting it up of a height of 10 meters. Now that problem is not very hard because of the fact that both your displacement and your force that you're exerting are in exactly the same direction. And therefore the angle in between your force vector and your height vector in this case, which is your displacement, the angle between them is 0. So that means it's just a multiplication of the two magnitudes. And if you're going to be able to do that, well, you should know what the actual force that you would need to be able to take this box and actually, lift it up here for a certain amount of distance, in this case 10 meters, what that particular force would be. Well, that force is going to be equal to the actual weight of the box. You have to overcome that particular weight of the box in order to start lifting it. Where I'm assuming that, air resistance is negligible and there aren't any other kind of frictions or other forces present. So the weight of the box, which of course is down due to gravity, is simply mass multiplied by gravity itself. And therefore, since the mass is 10 kilograms, gravity is 9.8 meters per second squared. So if you multiply those, you're going to get, that's going to be 98 newtons, just 10 times 9.8. So that is the force that you're going to have to overcome. The weight is of course down because gravity is pulling it down, and that force has to be 9.8, 98, be careful there, 98 newtons up to overcome that particular force. And now from work, well, we can take work, which is going to be this right here. Well, the dot product is going to be just the multiplication of the magnitudes, because the angle between your height, which is your displacement, and your force that you're exerting, the angle is 0. So this is going to be, I guess, 98 times 10, which is 980. And that's the work that is needed. Now the question arises, all right, well, how would I figure out the work that needs to be done if you're going to be moving this box, okay, all the way up to the top? Because it looks like you're going to be lifting it the same amount in terms of the height, right? It's going to be at exactly the same level if you lifted that box just straight from the floor up. So it should show us that the work is actually identical being done. Well, let's take a look and break this down, and I want to show you how you can do that. So we need this. We basically need the force vector, and then we need the displacement vector. Well, that the displacement vector that I have, so from the bottom to the top, I can get by just using regular standard trigonometry. So notice we know the angle is 30 degrees and we know the height is 10 meters. So what I do know is, so this is 10, I'm going to just leave it as 10 meters, and I'm trying to find that distance. So this particular distance right here, what that distance is. Well, that's just my hypotenuse. So I know this, I know my angle, so of course I can figure this out. Because notice that sine of 30 or sine of theta is equal to opposite over hypotenuse. Well, opposite is equal to 10. My hypotenuse, I don't know what that distance is. I'll put capital H within there. Well, that's just simply equal to 10 divided by sine of 30. Now, if you remember your unit circle, sine of 30 is a half. And therefore, so my H is going to be 10 divided by a half, which is just 20 meters. So I have just found, so this right here, my displacement vector, so this is going to be that, and it is equal to 20 meters at, 30 degrees, okay, from the horizontal. This is all in meters. So I have my displacement vector. Now, what about my force? How would I find that? I'm going to move this over to the side. I don't need it for the moment. Well, in order to do that, I'm going to actually take this box, okay, right here. I'm going to duplicate it, make it a little bit bigger for us, and bring it down. Now, whenever you're dealing with any kind of a ramp, then do not forget that your weight is still applicable. So we do have our weight, right? So our weight that we have, I'm going to duplicate this. I'm going to bring it down. I'm going to make it kind of bigger here. Okay, let's make it much bigger. That weight is pulling this down. Now, of course, the ramp doesn't allow this box to fall through that ramp, right? And this W, so the actual weight that I have in here, that is 98 newtons, which I've already calculated. But I'm not going to have to overcome the entire 98 newtons because of the fact that some of it is being kind of pushed up by the actual ramp itself. That's just kind of from Newton's laws, okay, of for every action you get a reaction. And what we do in this case is, what I want to be able to see and overcome. This has several components. So notice that what I'm going to do is I'm going to kind of draw out the ramp here. Hopefully I can do that in some nice fashion. Okay, let me shift it over. I just want to move this over. All right, so that's my ramp. And with respect to this ramp, so now notice you're going to have components. Okay, so within here. So from here, I can drop down, okay, this right there. Now, what am I doing? What I'm actually doing is I'm dropping this down at a 90 degree. So this right here that I have right there, that is, let me just put this as, so this is 90 degrees, right? Now, that component of the weight, so that W is broken down into two pieces. It's going to have a component in this direction, which is trying to slide it down. And it's going to have a component in this direction, which is the dotted line, right? Which is trying to bring it against the actual surface. Now, we are trying to find the component which is in the direction of my displacement up the ramp. So I want to know this right here. I want to know this piece because I'm going to have to push or pull this box up the ramp right here to overcome this. So this is what I have to be able to find. Now, how would I do that? Well, again, I can just use trigonometry. It's not very difficult to be able to do that because of the fact that I know this angle right here. So if I know this angle, of course, and I just want to show you that I also know this angle, right? If this is 30 degrees, this right here is a right angle, that's 90. So this must be 60 degrees, this right here. Now, this weight right there, so that I have, okay, that is being pulled down, so straight down, right? So that's this line right here. It's like you would have that. This component right here is in the same component as my ramp. So I know this angle is 60. So this angle is 60. This angle is 30. And then this angle is just 90. So if I know those, so right here, so this is just 60 and this is 30. That's coming from the fact that I know this right there. And that will tell me that I can take my component right here, right? So take this, which is 98, and then take the cos to get this component right here. So this is by trigonometry. I want to know this piece, which is the adjacent piece, okay, right here to my 60. While cos of 60 is 1/2. So 1/2 times 98, that component is going to be 49 newtons, right? And this is at kind of, as you can see there, it's, you know, if you were thinking about in terms of the actual angle itself, so it's 49 degrees at, and I can start from south, all right? So I'm going to put this as south, and then I'm moving along, so 60 degrees, okay, within here, and that's going to be west. So that's the actual component that I have to overcome, which means just like I had to overcome the weight over here to lift the box up, so I had to overcome this weight which was down, so I had to overcome this with the same amount of force. I'm going to have to overcome this with the same amount of force in the opposite direction. So I need this force, which is going to be 49 newtons, but now in the opposite direction. And that direction, so this direction right here, so that's 49 newtons that I'm going to have to move this with. This is in the same direction as my displacement. And notice my displacement, so if I calculate my work, which is the force dotted, so the dot product with the displacement, the angle in between them now again is 0. So it's going to be 49 times 20. That's the actual work that needs to be done. It is 49 newtons multiplied by 20 meters, which again, as you can see there, it is going to be 980, which is the same as just lifting the box up. Now, I do make the assumption that there is no friction on the ramp. Now, that's highly unlikely that you have a frictionless surface. But when you're just studying this and you're getting introduced to vectors and work in particular, either in physics or maybe in a vectors class, or, you know, if it's a component of your calculus class or something like that, then you will assume that there is no friction. Now, they can of course tell you that there is friction. Now, if there was friction, you would have to exert more force to get this box to move. But to get it to move up the ramp, you just have to overcome gravity, which is the weight of that box. So you have to be pushing or pulling this with 49 newtons to break through, right? To make it so that it's no longer static and just sitting there, and now it just starts to be dynamic and it starts to move. And you do notice that the two ways of calculating work are going to give you the same result. This is a really nice exercise because it shows you the power of vectors. It shows you the need for understanding trigonometry, having some kind of a visualization of being able to work with these triangles. And if you do work with them more and more, those components that you're breaking down your forces, like I did, for example, right here, are going to hopefully become a lot more obvious to you. This is just one of many examples. But visualizing and doing these body diagrams, that's what they're called. You have a body, okay, some object, and you start putting your vectors in various directions, and then you're trying to see which vectors apply to the problem at hand. So that is it for this example. I do hope that you find it useful. It's another application of really vectors, dot products applied to calculation of work. Thanks for watching. We'll see you in future videos. Happy studying. Bye, everybody.